Hi, everyone. Thanks for joining us for the C2SMART webinar series. I'm John Patinos, a project manager at C2SMART. As a heads up, this webinar is going to be recorded and uploaded to the C2SMART YouTube channel with our recorded seminars and all of our other webinars. If you have any questions for our presenters today, please feel free to use the Q&A button at the bottom of the screen in Zoom, and we'll answer them live at the end of the webinar. So today's webinar is the second one related to C2SMART's work on the interactive real-time COVID-19 data dashboard, which aggregates various transportation data sets to analyze and display trends in the wake of COVID-19. Today I'm with my colleagues Fan Zuo, Dr. Jingqin Gao, and Yubin Shen. So Fan is a doctoral student in the Transportation Planning and Engineering program at NYU Tandon and a researcher at C2SMART, whose work on image processing and computer vision we'll speak about today. Dr. Jannie Gao is a postdoctoral associate at C2SMART, where she works with C2SMART Director Kaan Ozbay. Her research interests lie in offline and real-time simulation modeling, big data and machine learning approaches to transportation and transportation economics. And also with us is Yubin Shen, research engineer at C2SMART Center, providing technical support, whose work was crucial to the development and maintenance of the COVID-19 transportation data dashboard. So without further ado, Jannie, do you want to start?
Sure, thank you, John. So as John mentioned, today we're going to talk about the computer vision methodology that we developed to analyze social distancing trend under COVID-19 conditions, leveraging public transportation cameras. Fan, can you actually go into the display mode? Thank you. Next slide. So first of all, this is actually a great collaborative work between multiple team members that listed over here. We have Fan, Yubin, Mara, Omar, Dr. Ozbay, and we also have actually two undergrad students, Siva and Nick, who work from our NYU team. We have Abdullah from OTEC, which is a highly regarded engineering technical service firm, and also Professor Hong Yang and his student Qing Yu from Optical University. Next slide. So for the outline of this presentation, I'm going to start from the introduction and motivation of why we're doing this project, followed by the detailed methodology behind it, and also our offline and online applications. In addition, we're also going to introduce a GUI, a graphic user interface that we developed to train more data labels for future research work, and how we implement all of these in the back end. Next slide, please. So there's one term that people really has quickly become familiar with, is called social distancing from the start of the pandemic. And one thing that people start to realize is, to understand the relationship between social distancing and urban mobility are really crucial during the pandemic. And we also want to understand, what the new normal gonna look like of urban mobility amid the pandemic. Next slide, please. So for some of you who attended our webinar last month, you probably already know that a C2SMART Center has developed a highly interactive data dashboard for COVID-19 that kind of like pooling multiple open data sources to observe, travel trends and mode choice, as long as the effect of social distancing. And this data dashboard combine information from transit, ridership, speed, city bike information, recorded based information like parking tickets or speeding tickets. We also have a weighing motion station information that gave us some indication about freight traffic, and also like social distancing information that we grab from the traffic cameras. So here is the architecture of our data dashboard. By acquiring real-time data and offline data, we're able to process them and store them in our data warehouse and data lakes. And in the end, we have this cross-domain multi-data view of multiple data sources. And this data dashboard actually allowed us to do some simple data analytics in real time as well. And one of the important parts of this data dashboard is called sociability. This is a subboard that we have. So basically we have two boards. We have the mobility data dashboard, and we also have the sociability board. And today we're going to focus on what we did for this sociability board. Next one. So the challenge here is really about, we know that social distancing orders are announced since March, but it remains kind of unclear how people are responding to these policies. Wait, can everyone hear me? Just want to make sure, because I got a warning about my speaker. Okay.
It's a little bit staticky. I think it might be a function of the distance to your microphone, but otherwise we can hear you just fine.
Sure. Okay. I'm gonna just go continue on that then. So one thing that there are a lot of study talking about, like internal, talk about like indoor identification or indoor monitoring of like social distancing, but there are not many work actually about how to identify the density of the crowd on the street, especially those hotspots. For example, the corner of the intersection where people gather and waiting for the red light, or like bus stop where people actually line up and waiting for the bus. So this is the thing that we find important, that we want to understand the actual reduction in social contact and this kind of like safety rate, to measuring the effectiveness of the social distancing policy. And on the other hand, next slide, please. On the other hand, it's very hard to collect and measure social distancing. So from the aspect of researchers and also agencies, in order to collect this data, we will need to send people outside. And the challenge here is it is really unsafe to expose investigators to conduct field data collection. So one intuitive solution that we have on our mind is, what about leveraging those traffic cameras that are already out there? And for New York City, we have over 700 traffic cameras, and most of them are actually facing now urban streets, not facing the highway. So we are able to capture some of the pedestrian movement. But new challenges also come up that, each cameras may have a different angle and they move around. So it might be difficult to calibrate on every camera to get acceptable results. So based on all these complications, we come up with a deep learning based video processing algorithm, or we can call that computer vision based algorithm, that can help us to measure the social distancing using all these installed cameras. So first of all, this approach is inexpensive, especially for New York City, because we already have most of the cameras installed. Second, this computer vision based algorithm can help us to do real-time detection for different classes, not only the pedestrians, but also the cars, trucks, cyclists, the buses. And in order to overcome the difficulties of, like each camera have a different angle, we develop a distance-based projection and approximation method that even with different camera angles, we will be able to estimate the social distancing between a pair of pedestrians. And this helps us to get the temporal and also spatial density distribution. I want to mention like one of the biggest advantage is that it is fully remote and it's free of risk, as there's no requirement of any presence of human investigators in the field. And next, I think I'm gonna pass it to Van to talk about the details about the methodology.
Okay. Thank you, Jannie. So for the framework, or for the methodology, we propose to build automatically social distancing measuring framework using a low-cost, continuous, real-time localized traffic big data acquisition and a traffic-related object detection framework. So as you can see in the figure, this framework leverages hundreds of the traffic cameras from the New York City Traffic Management Center, and among with a deep learning based video processing method for analyzing time-dependent social distancing patterns in the outdoor environment at the local level without the need for new equipment or tools. So, object detection is applied to real-time traffic camera videos or stored videos collected from those multiple key locations within New York City to provide a holistic view of the evolving social distancing patterns during the COVID-19 outbreaks and the subsequent recovery process. So, so our data acquisition framework contains a multitask deep learning model and embedded convolutional neural network, which is CNN, and for the pedestrian detection and characterization. The simultaneous accomplishment of the multiple tasks will ensure its computational efficiency and inference performance for large-scale data collection practices. And our final data collection approach is free of the risk without any presence of human investigators in the field, and offers the opportunity to collect the massive amount of the perishable data to objectively and timely profiling the unique social distancing patterns using New York City as a living laboratory. So the core working framework of the social distancing data collecting is centered on the idea that one can obtain the density of the pedestrians and the distance between each pair of the pedestrians by using a pre-trained the object detection model and a real distance approximation and several post-processing filters. So the flowchart illustrates the workflow of the proposed methodology. So first, we will use the collected video as input, and the program will split the video into frames. After that, there are 4 major parts of the framework. Well, the first one is the pre-processing model, because the raw input can use some pre-processing to improve the performance of the object detection model, such as we can brightening the shadows, or we can correct the gamma to make the input better for the object detection models. And second, we will have the object detection model, which is one of the most important part. And then we will have the post-processing model, because the raw output from the object detection model will have some errors, such as duplicate detections, like the oversized detections, or detect at an impossible location, something like the vehicle in the air or something. So we will use the different filters to improve the detection accuracy and eliminate detection errors for this study. And there are one more filter called the relationship filter is used for the next model to get more accurate social distancing results based on the judgment between the pedestrians to find out if they are close to each other or not. Okay. So the next one is another the most important part, which is the real distancing estimation model. Okay, and I will introduce this part in detail later. And the last one is the analysis model to generate the data analytic reports online or offline based on the different requirements. Let's go to the first important model, the object detection model. Okay, when the input and the pre-processing have finished, the object detection model will start to identify the objects in each frame. The backbone architecture is the deep learning object detection model. In order to get better results from this part, we tested 3 different state-of-the-art model architecture, include the YOLO V3, the RetinaNet, and Mascar CNN. Okay, I will use a different type of word to describe why these 3 models. Okay, so the YOLO V3, like the rapier, is fast and it's accuracy, but sometimes it's too thin to dealing with the dirty words. And the RetinaNet is like a Viking sword, not so fancy, but stable. But of course, it is not that powerful. And the Mascar CNN is like a spy-hander. It's slow, but it's powerful. And it is good at identifying the overlapped objects. So in order to evaluate these three models, we use the non-max suppression. Because each model will provide a probability for each possible category and pick the category with the highest probability as a result. So we can consider the probability as a belief score from the model. The non-max suppression means if the confidence score is lower than some threshold, and the result will be dropped. For example, here, you can see in the picture, we have some scores, if you can see the scores. And if we set the 40% as a threshold, then the identified object car with the 35 confidence score will be dropped. Okay. So we will try different, the threshold to find out the best one, the best results, the best model. And the ground truth data for model evaluation and validation will manually label from the collected video data. And we use the peer curve, the computing cost, and the MAE result to decide which one is the best model for this research. And finally, you can, based on these plots, you can see the peer curve and the MAE scores here. We decide the YOLO-V3 as our backbone object detection model. And also the MAE is also used to identify the optimized non-max suppression threshold. And the experiment environment and the computing costs are also provided on the right side. And also the required language and the libraries are provided below. We use the Python, we use TensorFlow, Keras, and ImageAI as the environment and the libraries. Okay. Okay. So let's go to the next important part, the real distancing estimation part. Okay. The major challenge of detecting the social distancing pattern from the surveillance video is the accurate measurement of the actual distance between pedestrians in images. So the difficulties usually arises from the perspective effect and the lack of the reference. So a common method is computing homography, which is a matrix represents the transform between two planes that morph the video frames from perspective view into top-bottom view. Then we can use the presetting objects with known mirrors or existing objects with available mirrors as a reference to compute the distance in the transformed frames. And common reference obtaining method include the field visit, the measurement from the Google Maps or civil infrastructure documents, and a chessboard like a calibration plate like this. So since existing surveillance cameras is different at different locations, you usually have different angles and the different views of the perspective and may be repositioned at a different time. So it may be challenging to get a solid reference to calculate the distance using the camera feeds. Also, it is not safe to send our investigator to the field, right? So a generalized method that can be used to measure the distance from the multiple cameras is needed. In the light of these complications, we propose a novel method to measure the distance without field measure and the reference and the homography computing. So let's go to the next part. So initially, we can use a KD tree to quickly searching how many pedestrians in the image are close to each other using some threshold, because we don't want to compute too many pairs, because when you have a lot, like hundreds of people, you will have to calculate a lot, right? And after that, we slice the images into several hyperplanes, which are the perpendicular to the horizontal plane, and the points on the horizontal lines in the hyperplane always have the same distance to the observed point, which is the camera, right? So because of the perspective effect, the number of pixels in the image corresponding to the same real-world length can vary on different hyperplanes. In other words, each hyperplane will have a specific real and to pixel distance rate, or we can call it RP rate. And the further hyperplane, the larger RP rate, as you can see in the showcase here, the relationship between the green and the yellow hyperplane, right? The far away the object, you will find that is smaller, right? And the second, we assume that each person in the image is perpendicular to the horizontal plane and has the same real height h0. Because the detection results may be affected by the same height assumptions, but because of the size and the resolution of the videos, the impact of the same height assumption is acceptable. And next, we can identify the centroid of all bounding boxes of those detected pedestrians. As you can see in the last slide, each object will be pointed out by the bounding box. And after that, we can calculate the RP rate for each pedestrian and estimate the pixel distance between centroids of the bounding box and for each pair. For each pair, it is always available to find the two parallel hyperplanes perpendicular to the horizontal plane that the two pedestrians belong to. So the real distance between them is the integral of the unit RP rate multiplied the unit pixel distance. And after some transforms, we can use the approximated formula to estimate the real distance between pedestrian pairs. And here we can just use the real height, which we already assume to be a fixed number, and the pixel height we already get, and the pixel distance between the pair to calculate the real distance. Okay. So, okay, let's move to the application part. Like I introduced before, the framework can provide a different output according to a different purpose. So I will give some example to explain how to read and use the output to do the analysis. Okay. So the first one is the 24-hour temporal distribution of the pedestrian at one sample location, which is actually here is 5th Avenue and 42nd Street. This location normally has, an overall high and a consistent pedestrian density throughout the day before the pandemic, right? Just as a red dashed line here. Within the time elapsed, pedestrian density grows from the almost a straight line to as same peak patterns as pre-pandemic levels, right? You can see here the yellow to the green to the blue to the deep blue to the purple. It's just as the time moves. And during the pandemic, most detected pedestrian in the processed video frames we checked may be essential workers, and this can serve as a potential explanation for the peak observed in this dataset. And the second one is the box plot of average pedestrian density of each frame among different dates and the multiple locations together. Because we combine them like 10 different locations together to find out a general pattern, right? So the result shows a positive skew, meaning that the mean will be higher than the median, except for May 27, 2020, displaying a negative skew, and June 18, 2020, which is normally distributed. And a gradual increase in pedestrian volume is observed starting from the end of May and then it reached a stable status in the middle of from the middle of the June, and you can see after the middle of the June, it is not changing so much, and which means the pedestrian, the volume of the pedestrian and the performance of the pedestrians are staying at a stable state. Okay, the third one is the most important. No, the interesting one, the most interesting one. Yeah. So in order to identify the social distancing compliance, we generated the distancing distribution plots on the different number of pedestrians for a sample location in the different dates. So firstly, we categorized the video frames by the number of pedestrians, which means if the frame contains 5, we will combine them together as a one category. If it contains like 10 pedestrians in the frame, we will combine them together. And after that, we can compare the distancing distribution under the same conditions, right? Because we don't want to let the number of pedestrians to affect the distribution of the distance, because as you know, because the camera can just took a limited area. So if we have like 10 times of the like 100 pedestrians in the same in the limited location, the distancing between them, of course, will be limited, right? But we don't want that affect our results. So we categorize them by the number of the pedestrians. And you can see the plots shows the distribution are right skewed in April, which is the peak of the daily new cases reporting. And the distributions became flattened at the peak move, and the peak move left in May, because at that time it is the restore of the mobility, starting of the restore of the mobility. So people are starting to move out, but they are still learning to reform the distancing compliance. So which is so you can see the distribution here is flattened. And in June, the distribution became normal, normal again. I mean, the normal distributed again, but the peaks keeps moving left, which means that people are gradual reducing fear for the virus. But if you compare the June's pattern to the April's pattern, you still can find out that the peaks moving left, because people are okay to getting close to each other, right? But if we compare these two with the May, it's different, because you will find a little bit fat on the head or on the left for the May's distribution, and you can see some fat-tailed phenomenon on the April, because that is the highest point of the people's fairness, right? Okay, so we also have some heat maps. The heat maps will highlight the hotspots that the pedestrians are close, are in the close contact. In this plot, we use the 12 feet as a threshold, and it is important to mention that this heat map do not represent the pedestrian densities. Okay, instead, they illustrate the detection areas that capture a distance less than 12 feet between two pedestrians, which means it is a cumulative effect. So constructing this heat map will improve the classification of the social distancing guidelines accordance by focusing on areas that show the highest occurrence of pedestrians standing dangerously close to each other. In other words, generated heat maps operate as an attention mechanism for understanding and identifying the areas with a high risk of disease spread. Okay, so from the plot you can see where does people getting close to each other. There are some bus stops. There are the two starting and end of the crosswalk and something like that, and the pedestrian close to the at the end of the pedestrian walkway, right? So the policymaker can use this to adjust their policy to perform their to implement the rules better. Okay. And also this is a online output example. It will provide some real-time quick analysis and the useful plots based on the requirements. But Yubin will introduce this framework in details. So I will leave this part to him. Okay, so also we have, Jannie just mentioned that we have a GUI. This is for the training data labeling. So the reason that, because if you remember, the object detection model for using the deep learning object detection model is pre-trained by an existing image database, which is a COCO database. It contains tons of the images for the training purpose. So we can save our time on the training part, but there are some limits for if we use the pre-trained model, which means if we use the prepared image dataset, because of these limits I showed here, if we will have the camera angle bias, which because our images from the New York City DOT is from the bird view level, but most of the images in the training dataset are at the street view level, which is different angle of the object will give you different information. So using those using those images to train the model will not give you a very good performance of the images we get in the from the New York City DOT, right? And the second thing is a category bias, because the COCO dataset contains tons of the images under the person's label, which is it has a lot of person's pictures, but it'll just have like 10,000 of the images with vehicles and only 1,000, maybe 2,000 images with bicycle, the bus or trucks in the specific category. So this means that the pre-trained model is biased because the model will identify the person way more better than identify the truck, identify the bicycle. But the bicycle, the truck, and the buses is also important for us for in the futures, the research, right? And the third one, the local characteristic bias, because New York City has a different model of the bus and the trucks. So if we use the bus and the trucks from the worldwide, the images from worldwide models, it will not identify the bus in the New York very good. Okay, so retrain the object detection model by some localization data will improve the performance significantly. So thanks to our outstanding undergraduate interns, Murad and Omar, we have a GUI to labeling our local images. Now, as you can see in the demo, we have a really easy to understand GUI here. You just need to click the different type, and you select the objects in the image, you can save them, and you can get the output from the GUI and use that as, and the output will be transferred to the directly to use training mode. So you can use the output directly to train your model. And also, if you remember, we have some pre-processing in our algorithm, in our framework, such as the gamma correction, the shadow brightening, something. And we also added those functions into the GUI. So we can pre-process the images directly using those functions. Okay, I'll pass this one to Yubin. Yubin?
Okay, thank you, Fan. So I will introduce the implementation of this application. So before I run into the implementation details, so I want to introduce the Docker first. So let's go to the next slide. So what is Docker? So the Docker is an open platform for developing, shipping, and running applications. So it's you can consider the Docker as a OS level virtualization. So the Docker works like the virtual machine, and you can install whatever software inside. But I mean, compared to the virtual machine, so the Docker is more lightweight. So let's take an example. So if I say that we want to install, we want to make a PHP website. So if we only use the host machine, so we have to install the PHP, install the Apache, and install the MySQL database. And then you have to configure everything and then make the connection work. So that's for the thing without the Docker or virtual machine. However, if you use Docker, so you can just import the existing environments. So I mean, in the Docker Hub, they have plenty of existing environments. So you don't have to, deploying them one by one. So they saves you a lot of time. So also they give you more focus, makes you more focused on the application coding rather than the environment setup. So it's very convenient. And also one more advantage is like your host machine is very clean. So previously I have the experience like after you install some dependency or install some library, they have a confliction with the existing application in your in your desktop or in your the server, and they make you crash, and you have to roll back. So it takes you a lot of time. But for the Docker, so you don't care about that thing because everything is inside the container. So in short, the Docker is a big container. So it's so they contain everything inside the thing. So it's you warp everything inside the box. So your host machine is clean and safe. So let's go to next slide. Okay, so I want to mention more benefits for the Docker. So here's the comparison with the Docker and virtual machine. So I think the biggest differences between the Docker and the virtual machine is how the resources are assigned. So for the virtual machine, like you can see on the right side, so everything is fixed. You have the fixed CPU power, you have the fixed memory, and the fixed network access. However, sometimes the resources are not, are wasted, so it's not fully used. So let's say that maybe your application only use 50% of the CPU power, and the other 50% is wasted. So it's not good. So also the virtual machine they cause a lot of system administration work and also the operation work. So you have to assign more people, or you have to spend more time on those kind of thing. But Docker is more lightweight. So everything is inside the Docker environment. It's more flexible if you want to just twist it, or you want to just adjust some settings or cooperate some modules and make them work together. So normally, another good benefit for the thing is the Docker containers, they are unprivileged. So which means that they could not get access to your host machine, or they could not change the configuration of your host environment. So that makes Docker more secure. It's also, this good thing for the developer or for the administrator to maintain the whole system. So, but here, I don't want to say that Docker is better than the virtual machine. So sometimes the advantage can be drawback. So, I mean, in some, I will show an example later on, but here I will say that the more details are out of the scope of today's presentation. So, I mean, if everybody, anybody is interested in the details, maybe you can reach out to me so we can discuss it more. But today, I will just explain some examples. So I want to explain the detail for the comparison between the Docker and the virtual machine. So let's go to the next slide. So here, I also want to mention that the difference between the GitHub repository and the Docker image. So here's I list some comparison. So here we all know that there are a lot of good open repositories in the repository in the GitHub. So, but I mean, sometimes the quality of the documentation is different. So, for example, for a lot of I mean the image processing library, so their documentation is not friendly for the beginners. So you have to have some background knowledge before you can read their documentation. However, for the Docker image, so you do not need to understand everything behind the code. So you can just run the image and get the result immediately. So it's very easier for user to start. So I mean, sometimes we just want to test some application rather than we understand everything. We don't want to be expert for everything. And Docker give you that convenience for you to just run the things fast. And if you find the result is very interesting, and then you can just follow up and learn some technology or read more documentation behind the implementation. So that will be another good point for the Docker. So after we talk about everything about the benefit of Docker, so we go into the detail of the implementation. So let's go to the next slide. So here is the how we implemented the Docker into our system. So we have a server, and inside the server we have a Docker environment. So we customize the official TensorFlow Docker image and build our own container to run the application. So the application will collect the raw images from the DOT camera website, and we have a fixed interval. So let's say that every 5 seconds, I say every 5 seconds they will collect the raw image and feed them into the application. And the application will export the predict image, and then the Nginx proxy server will serve those latest image to our website. So I want to I need to speed up a little bit. So I also want to mention some bottleneck for this application implementation. So the first thing is like we need to find the balance between the accuracy and the speed for the real-time processing, because finally we want everything to be real-time. But like Fan said before, so we have a different prediction module. So we have to choose the balance between the speed and the quality. And also, our server only have the CPU. We all know that a lot of AI processing or the machine learning, they need a GPU. But for our server, we only have a CPU. So this also be a bottleneck. So we have limited compute power. Also, we have to think about the frequency. So if we make the things too frequent, I mean, they will harm other applications in the server. So we have to control the balance. So let's go to the next slide. So here is an image where from another paper. So they give a benchmark for the accuracy and the FPS, the image they can process per second. So that will be some reference for you guys if you are interested in which kind of module are best for your prediction or best for your application. There will be some references. So let's go to the demo. Okay, so before the demo, I want to mention two things. So it's the first thing is like this demo is not available on our website right now because we need agreement from the DOT. So this one is only for research purpose. And the other one I want to mention is like because the bottleneck I said before. So we control the refresh mechanism like 10 seconds as the interval. So you can see there will be some delays between the actual website and our website. That's because we set the different interval than the original website. But I mean, from the video, you can just check that the thing will be updated every 10 seconds and it's almost real time. So I mean, if we can get more, I mean, CPU or GPU power, and we can just reduce the frequency and the output will be more real time. So that will be my part. I think I already over the limit. So let's go to the Q&A section.
Thank you, Yubin, and also thank you, Fan and Jannie. That was great. So we have a couple of questions that have come in while you were presenting, but I would welcome all participants to start to type in your questions in the Q&A box at the bottom of your screen. So we will start with the first question that came in. How is this object detection different maybe from the object detection that Tesla is using for their FSD, their full self-driving computer? I don't know if you know the particulars of this.
Yeah, let me answer the question. So I did some research for that. So two things. One is the devices are different. So like Fan said, the camera we use like a bird view. But I mean, for the Tesla or some self-driving module, so they use a 3D sensor, like two cameras, at least two cameras. Because you know that one camera, even you can just measure the distance, there will be some error inside. But if you have two cameras, so you can make a triangle, so you can measure the distance more accurate. And also the self-driving, they have more sensors like the distance sensors or the infrared sensors and to a lot of other things. They work together to make the FSD. So this more complicated than our algorithm or our module.
I want to just add to what Yubin said. So I think the objective is also very different because, I mean, for Tesla, of course, like, you know, safe driving is one of the objectives they want to achieve. And as Yubin said, they actually use multiple sensors, you know, not just like vision, but they also have like LiDAR to kind of do this 3D projection. So they really want this kind of like high accuracy. But in terms of our application, we kind of like don't really care, you know, if we detect 500 people or 502 people, you know. So it's more about like the order of magnitude, as long as we get an estimation of the density that kind of serve the purpose. And the other, I would say like limitation here is also because the traffic camera videos, they are kind of like low resolution. So we are not be able to actually kind of identify, you know, the depths at the accurate depths of the angle. But in terms of the purpose of density estimation, or, you know, just like a kind of like 80% accuracy of object detection, it served the purpose.
Okay, I know you mentioned that maybe there was some difficulty in identifying certain objects, like truck classification, maybe. The question is, can this methodology be applied to identify different truck classifications? For example, number of axles, axle spacing, vehicle length, or truck type, like dump truck, trailer truck, or bus?
Yeah, let me answer this. Yes, of course. If you feed the model different information from different model of the trucks, like a different axle number or something, because you know the model can identify different parts of the truck. If they have wheels, multiple wheels, the model can tell you how many wheels there. So of course, they can identify different models of trucks. Yes, but depends on the training data set.
Are there any objects that this methodology has particular difficulty with? So for example, fire hydrants, children, not that children are objects, but, you know, smaller humans, large coats on people.
Yeah. they have the multiple. The text is different. We just use the transportation related labels. They also contains different categories.
Yeah, let me add one more point. So I think so two things. One is depends on the module, like the framework you use. So I think we use a YOLO v3. So the accuracy will be is not so good as the mask RCNN. So that will be limited some kind of like your prediction result. And also, like I said before, so we limited on the CPU power or the compute power. So if we have a more power and more time you use to predict, of course, the more accuracy you will get. So that will be a balance.
Have you thought of sociological applications to this research? For example, identifying distance maintained by close friends or partners versus strangers.
Yeah, this is a hard part of our work. We're still working on this, and it's hard to identify if they are close to. They know each other, so they stay together. They stay close to each other. But we're trying to use some networking models to try to figure this out. But it is hard because we don't have the ground truth, right? So that's why we use the number of pedestrians to categorize those frames to try our best to eliminate this effect.
Okay, another question about potential applications. How might this be used to estimate attendance at informal events, large informal events, such as people gathering in a park?
Yeah, for now it is hard to do.
Yeah. Okay, same answer. Okay, so while I have one more question. So last call for questions from the audience. Oh, we have one right here that I'll read first. Can we use depth estimation to find the distance between people, such as monocular depth estimation?
Yes. Yeah, but because the data we get is too simple. So we can use what we have, but of course you can use the molecular depth estimation. Yeah, but also it depends on the angle. Sometimes because the traffic camera's angle is not good to implement the molecular depth.
Yeah, this is another good question. In addition to the object detection that you've been speaking about, are you able to extract trajectories as well? So the application would be for conflict analysis, vehicle to vehicle or vehicle to pedestrian.
Yeah, I'll answer this one. Sure, but depends on the quality of the input. Yes, we tried this before because the image from the New York City DOT is like every 5 seconds or 10 seconds. It is hard to track them, to track the same objects between the frames. But if we have the continuous video, like 10 FPS or higher, we can do the tracking thing better or way more better. But for now, we can do that, but the performance is not as good as we want. Yeah.
So just add to what Fan said, we actually tried that for, you probably noticed that we're doing pedestrian density estimation, but we also actually try to do like pedestrian tracking. So we'll be able to do pedestrian counts instead of just the density like per frame. And that's one of the difficulties that we found, it really depends on the input, as it's not just because of like DOT's cameras, it's also because of the bandwidth that they're transmitted this information about, how well NYSWing Wi-Fi network works at that time, and also the transmission between NYSWing, TMC to the public web page. So if we're able to get like high resolution or continuous video, we can definitely do tracking of vehicles, tracking of pedestrians, doing like counts, also doing like speed estimation. There are a lot of things that we can actually do, besides just social distancing estimation. But just without any additional investment, I would say, to the current camera system, this is what we can do at the moment. But I would say, like, if we find this approach is actually very valuable, to the agencies, especially in the kind of like aftermath of pandemic, I feel like maybe within a small like investment of better cameras, and just mention we have the connected vehicle project where we actually have high resolution cameras and like continuous video. So for those locations, definitely what you mentioned is like it's possible to do, and I think they will be very valuable in the future.
Okay, so what is next for this research, and why are you excited about it?
Okay, I guess I'm gonna just jump in talking about that.
Go for it, yeah.
So we actually have a lot of ongoing work that we didn't really mention in the presentation, but there are a lot of things that we're thinking of, expanding this work. First of all, the result that we're showing is based on some selective locations. We actually collect, since the start of the pandemic, from March and April, we actually collect more than 100 locations of information. And I think one thing that we can do is we're going to expand the scale to kind of like large scale, so that covers not only, just specific location in Manhattan or Brooklyn, but kind of like cover all 5 different boroughs in New York City. And we also have some information from other cities like Seattle that we can take a look as well. So this will kind of give us a large scale, kind of like a more reliable estimation of the density. And the other thing that we've been discussing about is this is like outdoor application. We also think about like indoor application, like classroom, density estimation, or even like detecting, people wear face masks, this type of thing. And the other approach, which is very different than the social distancing work that we're doing, is, there's all different kinds of things happening on the curb, and this curb becomes really competitive right now. And we're thinking of using object detection also to help us to do a new generation of data collection in this field, that without sending any people to the field, we're able to collect different type of curb related data, not just because of like parking occupancy, but also maybe like illegal parking behavior, or like violation on bus lane, violation on bike lane, and maybe like even some open street information, if we'll be able to detect, like open restaurant or open street activity on the street. So these are all different kinds of direction that we're thinking of. We're already working on some of these, and hopefully we'll be able to soon to present some of the result of this continued work.
We have time. Another question got sneaked in right in the last minute. Why the choice to use YOLOV 3 when YOLOV 5 is also available?
Yeah, because when we do this project, YOLO 5 is not coming out.
Right, I think we have YOLO 4 at that time. We test both YOLO 3 and 4.
It is too fast in the half of the year. 4 and 5 comes out. Yeah. We will try the 5 later.
Okay, excellent. All right, so that's a wrap. Thank you, Fan, Jannie, and Yubin for speaking with us today. Thank you, everyone, for joining us. I definitely encourage you, if you enjoyed this, to follow C2SMART on Twitter, join our LinkedIn group and mailing list, and you can check out this webinar and all of our other webinars recorded on our YouTube channel. Thank you, everyone.
Thank you.
Thank you. Take care.
Bye.